Dear students, welcome to the lecture on torsion analysis of non-circular bars using Prandtl's method. This lecture will be covering part 1 of module 6 of the course Advanced Mechanics of Solids. In this lecture, I'll be explaining about the Prandtl's method. Here, I will begin with introducing you to Prandtl's stress function. Then I will derive the governing equations for the torsion analysis of non-circular shaft using Prandtl's method, and I will show you how Prandtl's method can be used for the torsion analysis of non-circular shaft. In the next session of this lecture, I will explain how Prandtl's method can be applied for the torsion analysis of circular shaft and elliptical shaft. And finally, in this lecture, I'll be explaining the Prandtl's membrane analogy. Consider a non-circular shaft of uniform cross-section as shown in the figure. It is subjected to a torque T, and the reference coordinates x, y, and z are as shown in the figure. R is the cross-sectional region bounded by the curve S. The stress state at a point P whose coordinates are x, y, and z is given by sigma xx is equal to sigma yy equal to sigma zz equal to tau xy equal to 0. The existing stress components are tau zx and tau zy. The Prandtl's stress function phi is defined as tau zx is equal to dou phi by dou y and tau zy equal to minus dou phi by dou x. The stress components should follow the equilibrium equations, which are given by dou sigma xx by dou x plus dou tau xy by dou y plus dou tau xz by dou z equal to 0, dou tau xy by dou x plus dou sigma yy by dou y plus dou tau yz by dou z equal to 0, and dou tau xz by dou x plus dou tau yz by dou y plus dou sigma zz by dou z equal to 0. The variation of shear stress along the z direction is 0, which gives dou tau xz by dou z equal to 0 and dou tau yz by dou z equal to 0. Since tau zx and tau zy are the only existing stress components, the above set of equilibrium equations gets reduced to dou tau xz by dou x plus dou tau yz by dou y equal to 0. Substituting for tau zx and tau zy, from equation 1 we get dou square phi by dou x dou y minus dou square phi by dou x dou y equal to 0. This implies that all the equilibrium equations are satisfied by the Prandtl's stress function. Now, since tau xz and tau yz are the only existing shear stress components, the only existing shear strain components are gamma zx and gamma zy. According to the Hooke's law, the shear strain components gamma zx is equal to 1 by g into tau zx, and the shear strain component gamma zy equal to 1 by g into tau zy. Substituting for the shear stress components tau zx and tau zy in terms of the Prandtl stress function, we get the shear strain components gamma zx is equal to 1 by g into dou phi by dou y and gamma zy equal to minus 1 by g into dou phi by dou x. In this case, the only two relevant compatibility equations are dou by dou x of dou gamma zx by dou y plus dou gamma xy by dou z minus dou gamma yz by dou x equal to 2 into dou square epsilon xx by dou y dou z, and dou by dou y of dou gamma xy by dou z plus dou gamma zy by dou x minus dou gamma zx by dou y equal to 2 into dou square epsilon yy by dou y into dou z. Here, dou gamma xy by dou z equal to 0, dou square epsilon xx by dou y into dou z equal to 0, dou gamma zy by dou x equal to 0, and dou square epsilon yy by dou y into dou z equal to 0. So the compatibility equations become dou by dou x of dou gamma zx by dou y minus dou gamma yz by dou x equal to 0, and dou by dou y of dou gamma zy by dou x minus dou gamma zx by dou y equal to 0. Writing the strain components gamma zx and gamma zy in terms of the Prandtl stress function phi, the above equations become dou by dou x of dou square phi by dou x square plus dou square phi by dou y square equal to 0, and dou by dou y of dou square phi by dou x square plus dou square phi by dou y square equal to 0. This means dou square phi by dou x square plus dou square phi by dou y square equal to a constant. For the time being, we'll name the constant as f. So far, we have applied the equilibrium equations, Hooke's law, and the compatibility equations. Now, we'll apply the boundary conditions. The boundary condition equations are given by sigma xx into nx plus tau xy into ny plus tau xz into nz equal to x bar. Tau xy into nx plus sigma yy into ny plus tau yz into nz equal to y bar, and tau xz into nx plus tau yz into ny plus sigma zz into nz equal to z bar, where nx, ny, and nz are the direction cosines of a point on the boundary of the cross-section. X bar, y bar, and z bar are the externally applied forces along the x, y, and z directions respectively. We know that in this case, the only externally applied load is the torque T. So the external forces along the x, y, and z directions are 0. So x bar equal to 0, y bar equal to 0, and z bar equal to 0. Also, we have the stress components sigma xx, sigma yy, sigma zz, and tau xy equal to 0. For a point on the boundary of the cross-section, the direction cosine nz equal to 0 since the cross-section is perpendicular to the z-axis. The direction cosines nx is equal to dy by ds and ny equal to minus dx by ds, which we have already seen in the Sven-Venens method. Out of the three equations for boundary conditions, only the third equation exists because all the terms in the first two equations are 0. Substituting for the direction cosines nx and ny in the third equation for the boundary condition, we get dou phi by dou y into dy by ds plus dou phi by dou x into dx by ds equal to 0, which means d phi by ds equal to 0. That is, phi is a constant around the boundary. For solid section, phi is 0. That is, phi equal to 0 along the boundary for a solid section. Now, we will see the moment due to the shear stresses at point P. It is given by tau zy into x minus tau zx into y, as can be seen from the figure. The net moment due to the internal stresses is given by double integral over the region R tau zy into x minus tau zx into y into dx into dy. This net moment should be equal to the externally applied torque T, which gives T equal to double integral over the region R tau zy into x minus tau zx into y into dx into dy. Writing the stress components tau xz and tau yz in terms of the Prandtl stress function phi, the above equation becomes applied torque T is equal to minus double integral over the region R x into dou phi by dou x plus y into dou phi by dou y into dx into dy. Adding and subtracting 2 phi within the square brackets, the above equation becomes T is equal to minus double integral over the region R x into dou phi by dou x plus phi plus y into dou phi by dou y plus phi minus 2 phi into dx into dy. That is equal to minus double integral over the region R dou by dou x of phi into x plus dou by dou y of phi into y minus 2 phi into dx into dy. Opening up the square brackets, the above equation becomes T equal to minus double integral over the region R dou by dou x of phi into x plus dou by dou y of phi into y into dx into dy plus twice double integral over the region R phi into dx into dy. Using Gauss divergence theorem for 2D, the first integral in the above equation can be written as a line integral along the boundary. Thus, the above equation becomes applied torque T is equal to integral over the boundary S phi into x into nx plus phi into y into ny into ds plus twice double integral over the region R phi into dx into dy. We have already seen that the Prandtl stress function phi along the boundary for a solid section is 0. So the first integral along the boundary becomes 0. Thus, the applied torque T is equal to twice double integral over the region R phi into dx into dy. Now, we will find out the expression for the constant F on the right hand side of equation 3. Equation 3 is dou square phi by dou x square plus dou square phi by dou y square equal to F. Consider the left hand side of the above equation. Dou square phi by dou x square plus dou square phi by dou y square, which can be written as dou by dou x of dou phi by dou x plus dou by dou y of dou phi by dou y. Substituting for dou phi by dou x and dou phi by dou y from equation 2, the above equation becomes dou square phi by dou x square plus dou square phi by dou y square equal to g into dou gamma zx by dou y minus dou gamma zy by dou x. Now, substituting for gamma zx and gamma zy using the strain displacement relations, that is gamma zx is equal to dou u by dou z plus dou w by dou x and gamma zy is equal to dou v by dou z plus dou w by dou y. The above equation becomes dou square phi by dou x square plus dou square phi by dou y square equal to g into dou by dou y of dou u by dou z plus dou w by dou x minus dou by dou x of dou v by dou z plus dou w by dou y. Expanding the terms within the square brackets and cancelling out the terms plus dou square w by dou y dou x and minus dou square w by dou y dou x, we get dou square phi by dou x square plus dou square phi by dou y square equal to g into dou square u by dou z dou y minus dou square v by dou z dou x. The above equation can be written as dou square phi by dou x square plus dou square phi by dou y square equal to minus g into dou by dou z of dou v by dou x minus dou u by dou y. While studying the strain displacement equations in module 1, we have studied that the rotation about the z-axis omega z is equal to half of dou v by dou x minus dou u by dou y. So dou square phi by dou x square plus dou square phi by dou y square equal to minus 2g dou by dou z of omega z. Now dou omega z by dou z is the rotation per unit length of the shaft, which is theta. So we have dou square phi by dou x square plus dou square phi by dou y square equal to minus 2g theta. Thus, the constant term f in equation 3 is minus 2g theta. Now, let me summarize the Prandtl's method which we have learned. For solving a torsion problem of a non-circular solid shaft, we have to find out a suitable stress function which satisfies the conditions phi equal to 0 along the boundary of the cross-section. Also, the applied torque T should be equal to twice double integral over the region R phi into dx into dy. Once a suitable stress function phi which satisfy conditions 1 and 2 is found out, the angle of twist theta can be found out using the equation dou square phi by dou x square plus dou square phi by dou y square equal to minus 2g theta. Also, the shear stress components tau zx and tau zy can be found out using the expressions tau zx is equal to dou phi by dou y and tau zy is equal to minus dou phi by dou x. Now we will use the Prandtl's method which we have learned for the torsion analysis of a circular shaft. Consider a circular shaft which is subjected to a torque T. The cross-section of the circular shaft is shown in the figure. Capital R is the radius of the shaft. Since capital R notation is used to represent the radius of the shaft, the region of the cross-section is represented by R bar. S is the boundary of the cross-section. P is a point at a distance small r from the center, whose coordinates are x, y, and z. Using the Prandtl's method, we will derive an expression for the shear stress components tau xz and tau yz at point P. Also, we will find an expression for the angle of twist per unit length theta. As we know, the expression for the circle is given by x square plus y square equal to r square. The Prandtl stress function phi for the circular section is taken as phi is equal to m into x square plus y square minus r square. From this equation, we see that if we substitute any point on the boundary, we will get phi equal to 0. Thus, the Prandtl stress function phi equal to m into x square plus y square minus r square satisfies the condition phi equal to 0 along the boundary of the cross-section. In this expression for phi, m is a constant. Differentiating, we get dou square phi by dou x square equal to 2m and dou square phi by dou y square equal to 2m. Substituting these expressions in the equation dou square phi by dou x square plus dou square phi by dou y square equal to minus 2g theta, we get 4m is equal to minus 2g theta, or m equal to minus g theta by 2. Thus, the expression for the Prandtl stress function phi for circular section becomes phi is equal to minus g theta by 2 into x square plus y square minus r square. To determine the angle of twist per unit length theta, we use the expression applied torque T is equal to twice double integral over the region phi into dx into dy. Substituting for the expression for Prandtl stress function phi, the above expression becomes capital T is equal to minus g theta double integral over the region r bar x square plus y square minus r square into dx into dy. Consider the cross section shown in figure. The area of the annular region shaded is given by 2 pi r into dr. If we integrate this expression from small r is equal to 0 to small r is equal to capital R, it will cover the entire cross-sectional region r bar. Thus, the integral expression double integral over the region r bar x square plus y square minus r square into dx dy becomes integral 0 to r x square plus y square minus r square into 2 pi r dr. Thus, the applied torque T is equal to minus g theta integral 0 to capital R x square plus y square minus capital R square into 2 pi r dr, which is equal to minus g theta into 2 pi into integral 0 to capital R cube minus capital R square into r dr. Integrating the above expression and applying the limits, we get the applied torque T is equal to minus g theta into 2 pi into r raised to 4 by 4 minus r raised to 4 by 2. That is, T is equal to g theta pi into r raised to 4 by 2, which gives applied torque T is equal to g theta pi into d raised to 4 by 32, where small letter d represents the diameter of the circular cross-section. We know that for a circular cross-section, pi d raised to 4 by 32 represents the polar moment of inertia IP. Thus, the applied torque T is equal to g theta into IP, which gives T divided by IP equal to g theta. Now, for finding out the shear stress components tau Zx and tau Zy, we use the Prandtl stress function phi. Phi is equal to minus g theta by 2 into x square plus y square minus r square. The shear stress components are given by tau Zx equal to dou phi by dou y. Substituting for phi, we get tau Zx is equal to minus g theta into y. The shear stress component tau Zy is equal to minus dou phi by dou x. Substituting for the Prandtl stress function phi, we get tau Zy equal to g theta into x. The resultant shear stress at point P is given by tau is equal to square root of tau xz square plus tau yz square. Substituting for the shear stress components tau xz and tau yz from the above expressions, we get shear stress tau is equal to g theta into square root of x square plus y square. We know that at point P, which is having coordinates x and y, square root of x square plus y square equal to r square. Thus, the shear stress tau is equal to g theta into r, or tau divided by r is equal to g theta. Thus, for a shaft having a circular cross-section which is subjected to a torque T, we get T divided by IP is equal to tau divided by r is equal to g theta, where IP is the polar moment of inertia of the circular cross-section, tau is the shear stress at point P, which is at a distance r from the center, g is the modulus of rigidity of the material, and theta is the angle of twist per unit length. Now, we will apply the Prandtl's method for the analysis of an elliptical shaft which is subject to a torque T. Consider an elliptical shaft having a cross-section as shown in the figure. 2A is the semi-major axis and 2B is the semi-minor axis of the elliptical shaft. R is the region bounded by the closed elliptical curve S. The equation for the elliptical boundary is given by x square by a square plus y square by b square equal to 1. The Prandtl's stress function for the elliptical section is taken as phi is equal to m into x square by a square plus y square by b square minus 1. Taking the partial derivatives, we get dou square phi by dou x square equal to 2m by a square and dou square phi by dou y square equal to 2m by b square. Substituting these expressions in the equation, dou square phi by dou x square plus dou square phi by dou y square equal to minus 2g theta, we get 2m into 1 by a square plus 1 by b square equal to minus 2g theta. From the above expression, we get m is equal to minus of a square b square by a square plus b square into g theta. Thus, the Prandtl stress function for the elliptical section becomes phi is equal to minus of a square b square by a square plus b square into x square by a square plus y square by b square minus 1 into g theta. The stress components are given by tau zx is equal to dou phi by dou y equal to minus 2 into a square by a square plus b square into g theta into y, and shear stress component tau zy is equal to minus dou phi by dou x equal to 2 into b square by a square plus b square into g theta into x. Here we will equate the externally applied torque to the moment due to the internal stresses, and we get applied torque T is equal to double integral over the region R tau zy into x minus tau zx into y into dx into dy. Substituting for the stress components tau zy and tau zx, we get applied torque T is equal to double integral over the region R b square by a square plus b square into g theta into x square plus a square by a square plus b square into g theta into y square into dx into dy, which is equal to b square by a square plus b square g theta double integral over the region R x square into dx into dy plus a square by a square plus b square into g theta into double integral over the region R y square into dx into dy. We know that double integral over the region R x square into dx into dy is the second moment of the area with respect to the y-axis, which is Iyy, and double integral over the region R y square into dx into dy is the second moment of the area with respect to the x-axis, which is represented by Ixx. Thus we get applied torque T is equal to b square by a square plus b square into g theta into Iyy plus a square by a square plus b square into g theta into Ixx. For an elliptical section, the second moment of the area with respect to the x-axis is given by Ixx is equal to pi ab cube by 4, and second moment of the area with respect to the y-axis is given by Iyy is equal to pi a cube b by 4. Substituting for Ixx and Iyy in the expression for the applied torque, we get torque T is equal to pi a cube b cube by a square plus b square into g theta, from which we get the angle of twist per unit length theta is equal to T into a square plus b square by pi g a cube b cube. Now we have already derived the expression for the stress components tau zx and tau zy. Consider the expression for the shear stress component tau zx. Tau zx is equal to minus 2 into a square by a square plus b square into g theta into y. Substituting for theta in the above expression, we get tau zx is equal to minus 2 into a square by a square plus b square into g into t into a square plus b square by pi g a cube b cube into y, which is equal to minus 2 ty divided by pi a b cube. And the shear stress component tau zy is equal to 2 into b square by a square plus b square into g theta into x. Substituting for theta, we get 2 into b square by a square plus b square g into t into a square plus b square by pi g a cube b cube into x, which is equal to 2tx divided by pi a cube b. The resultant stress at a point can be obtained as tau is equal to square root of tau xz square plus tau yz square. Substituting for the shear stress components tau xz and tau yz, we get resultant stress tau is equal to 2t divided by pi a cube b cube into square root of b raised to 4x square plus a raised to 4y square. Now, to find the expression for the maximum shear stress, consider the equation for the ellipse. X square by a square plus y square by b square equal to 1, from which we can write x square is equal to a square into 1 minus y square by b square. Substitute the expression for x square in the equation for the resultant stress. We get tau is equal to 2t divided by pi a cube b cube into square root of a square b raised to 4 plus a square into a square minus b square into y square. From the above expression, we can see that tau will be maximum when y is maximum, that is at y equal to b. Thus, the maximum shear stress tau max is equal to 2t divided by pi a cube b cube into square root of a raised to 4 b square. That is, maximum shear stress tau max is equal to 2t divided by pi ab square. Here, the expressions for the shear stress and the maximum shear stress we have derived, we can see that it is the same as the one we have derived for the elliptical shaft using Sen-Venant's method. Now I will explain to you Prandtl's membrane analogy. Consider a thin homogeneous membrane like rubber which is stretched with a uniform tension F and fixed at its edges, which is having the same shape as the cross-section of the shaft in the XY plane. The membrane is subjected to a uniform lateral pressure P from below, and the membrane undergoes a small displacement Z in the Z direction, where Z is a function of X and Y. The equilibrium equation for the membrane is given by dou square Z by dou X square plus dou square Z by dou Y square equal to minus P by F. The above equation is analogous to the Prandtl's stress equation dou square phi by dou X square plus dou square phi by dou Y square equal to minus 2g theta. If the membrane tension F or the air pressure P is adjusted such that P by F becomes numerically equal to 2g theta, then the above two equations are identical. The analogies between the membrane and the non-circular shaft subjected to the torque are given by: first is the height Z of the membrane is numerically equal to the torsion stress function phi. The second analogy is that the membrane height Z remains 0 at the boundary contour, which is analogous to phi equal to 0 along the boundary of the non-circular shaft. And the third analogy is the slope of the membranes are equal to the shear stresses tau Zx and tau Zy. That is, dou Z by dou Y equal to dou phi by dou Y, which is equal to tau Zx, and dou Z by dou X is equal to dou phi by dou Z, which is equal to minus tau Zy. Finally, the twist moment is numerically equal to twice the volume under the membrane. The twist moment T is given by double integral over the region R 2 into phi into dx into dy. Since phi is analogous to z, we get t is equal to double integral over the region R 2 into z into dx into dy, which is equal to twice the volume under the membrane. The above four analogies between the membrane and the non-circular shaft are called Prandtl's membrane analogy for the non-circular shaft subjected to a torque T. In the concluding part of this lecture, we will see the derivation of equilibrium equation for the membrane. Consider the equilibrium of an infinitesimally small element ABCD of the membrane after deformation. The length of the sides AB and DC be delta x, and that of AD and BC be delta y. Let capital F be the uniform tension per unit length of the membrane. The value of the initial tension is very large. Even though the tension changes when the membrane is blown up by a small pressure P, this change in tension can be ignored as it is very small as compared to the value of the initial tension. The force on faces AD and BC is F into delta y. Consider the projection of the membrane onto the XZ plane as shown in the figure. As can be seen from the figure, at point A, the force F into delta y makes an angle beta with the x-axis. And at point B, the force F into delta y makes an angle beta plus delta b with the x-axis. Vertical component of the force at point A along the z direction is given by F into delta y into sine beta, which is equal to F into delta y into tan beta, because for small values of angle beta, sine beta equal to tan beta. The slope at point A for the curve AB is tan beta, which is equal to dou z by dou x. Thus, the vertical component of the force at point A along the vertical direction is equal to F into delta y into dou z by dou x. Since this force is acting in the downward direction, we give a negative sign. Thus, the vertical component of the force at point A along the vertical direction is equal to minus F into delta y into dou z by dou x. Similarly, the vertical component of the force at point B along the z direction is equal to F into delta y into sine of beta plus delta beta, which is equal to F into delta y into tan of beta plus delta beta. The slope at point B for the curve AB is tan of beta plus delta beta, which is equal to slope at point A plus variation of dou z by dou x with respect to x into delta x. That is, tan of beta plus delta beta is equal to dou z by dou x plus dou by dou x of dou z by dou x into delta x. Thus, we get the component of the force at point B along the z direction is F into delta y into dou z by dou x plus dou by dou x of dou z by dou x into delta x. The force on face DC and AB of the membrane element is F into delta x. Now consider the projection of the element onto the YZ plane. As can be seen from the figure, the force F delta x at point D makes an angle alpha with the x-axis, and the force F delta x at point B makes an angle alpha plus delta alpha with the x-axis. As in the earlier part, the component of the force F delta x acting on the face DC and AB in the vertical direction can be obtained as minus F delta x into dou z by dou y and F delta x into dou z by dou y plus dou by dou y of dou z by dou y into delta y. The resultant force on the membrane element along the z direction due to the tension on the edges is given by the sum of the forces on the faces AD, BC, DC and AB in the vertical direction. That is minus F delta y dou z by dou x plus F delta y dou z by dou x plus dou by dou x of dou z by dou x into delta x minus F delta x into dou z by dou y plus F delta x into dou z by dou y plus dou by dou y of dou z by dou y into delta y, which is equal to F into dou square z by dou x square plus dou square z by dou y square into delta x delta y. The force due to the inflating pressure P in the upward direction is given by P multiplied by the projected area of the membrane element onto the xy plane, which is equal to P into delta x into delta y. For the equilibrium of the membrane element, we should have the net force along the vertical direction equal to 0, which gives F into dou square z by dou x square plus dou square z by dou y square into delta x into delta y plus P into delta x into delta y equal to 0, which gives dou square z by dou x square plus dou square z by dou y square equal to minus P by F, which is the equilibrium equation for the membrane. With this, I am concluding this lecture on Prandtl's method. In this lecture, we have learned how Prandtl's method can be used for the torsion analysis of non-circular shaft. We have seen the application of Prandtl's method for the torsion analysis of a circular shaft and an elliptical shaft. And finally, in this lecture, we have seen the Prandtl's membrane analogy. Thank you, students, for your patient listening.